Thanks for listening. I am presenting on subject of Waste-Derived Carbon Quantum Dots for improving the photostability of perovskite solar cells to more than 1000 hours. My name is Yugesh Kumar. I am PhD scholar in the Department of Materials Science and Engineering of Indian Institute of Technology, Kanpur. My research area is related with renewable energy technology, which mainly based on renewable source of energy. On Earth, mainly two types of sources of energy found. First is renewable source of energy and other is non-renewable source of energy. Coal and petroleum are examples of non-renewable source of energy. When coal and petroleum are used, then they emit large amount of poisonous gases in atmosphere, which are very harmful for our living things. But solar energy, which is one type of renewable source of energy, never emit any types of poisonous gas or pollutant in our atmosphere. And it also available in sufficient amount at sea level in free cost. So solar energy is the best option for using in types of renewable source of energy. Solar energy comes from the sun. When solar radiation passes through the atmosphere, then due to the scattering and absorption by the dust particles and small molecules like water, carbon dioxide, oxygen, reduce the intensity of solar radiation and only we get the 1000 watt per meter square at sea level, which also called the AM1.5G solar radiation. Here, yellow region show the sunlight at top of the atmosphere and red region shows the solar radiation at sea level. Mainly solar radiation at sea level divided into three parts: UV region, visible region and infrared region. UV region found between 295 nanometer to 400 nanometer. Visible region found between 400 nanometer to 700 nanometer and beyond 700 nanometer infrared region of solar radiation found at sea level. To convert solar energy into electricity, we generally use photovoltaic solar cell. Photovoltaic solar cell is type of electronic device. The main part of photovoltaic solar cell is PN diode. When P-type semiconductor and N-type semiconductor are joined, then it is called PN diode. When P-type semiconductor and N-type semiconductor are joined, then it creates the depletion zone. And this PN diode is called in forward biased. In P-type is connected with positive terminal of circuit and N-type is connected with negative terminal of circuit. This PN diode is called in reversed bias and P-type is connected with negative bias and N-type is connected with positive bias. When large numbers of photons which are found in solar radiation incident on PN diode of photovoltaic solar cell, then these photons are absorbed by PN diode and are converted into electrons and holes. These electrons and holes are collected by electrodes of photovoltaic solar cell which are made of metals. When these electrons and holes flow in circuit, then it creates the electricity. This is the symbol of photovoltaic solar cell. When large number of photovoltaic solar cells are interconnected, then it forms the module. This is the monocrystalline silicon module. This is the polycrystalline module of photovoltaic solar cell, and this is the amorphous photovoltaic solar module. In recent years, perovskite materials are used as observer layer to fabricate the perovskite solar cells. Because silicon solar cells require high cost and complicated processing methods. This is the crystal structure of perovskite. ABX3 is the general chemical formula of perovskite, where A is monovalent cation, B is divalent cation, and X is halogen anion. To determine the crystal structure of perovskite, we generally used gold-dust tolerance factor. Gold-dust tolerance factors mainly depends on the radius of A cation and radius of B cation. When tolerance factor lies between 1 and 0.9, then it forms cubic crystal structure. When tolerance factor lies between 0.9 and 0.71, then it forms orthorhombic or rhombohedral crystal structure of perovskite. When tolerance factor lies below 0.71, then it does not produce perovskite crystal structure. There are many properties of perovskite materials due to which perovskite materials are used as absorber layer as semiconductor in perovskite solar cells. First, perovskite materials are earth abundant all over the world, so it is easily available. Second, it has good electronic properties like tunable band gap. It can vary the band gap by replacing A cation and B cation or halogen anion. So we can tune the band gap of perovskite. Second, it has good electronic properties like high absorption coefficient, high carrier mobility, and high diffusion length. Perovskite materials have direct band gap, so it can absorb maximum amount of light. So these are the properties of perovskite materials due to which it is used in perovskite solar cells. To fabricate perovskite solar cell, perovskite materials used as photoabsorber layer. Mainly three types of architectures of perovskite solar cells used to fabricate the perovskite solar cell. First is mesoporous NIP. To fabricate mesoporous NIP, firstly we take the FTO coated glass slide which act as substrate. On FTO, firstly electron transport layer is deposited, and after deposition of ATL, mesoporous layer is deposited. And after deposition of mesoporous layer, perovskite layer is deposited, which act as photoabsorber layer. And after deposition of perovskite layer, HTL whole transport layer is deposited, and on top of HTL, electrode is deposited. To fabricate the planar NIP, we remove the mesoporous layer, which are deposited after ATL in mesoporous NIP. To fabricate the PIN on FTO, firstly whole transport layer is deposited, and after deposition of HTL, perovskite layer is deposited, and after deposition of perovskite, electron transport layer is deposited, and on top of that, electrode is deposited. There are many advantages of using the perovskite solar cell. Since perovskite material available in low cost and it is based on solution based fabrication, so it has low fabrication and processing cost. It gives high efficiency because perovskite materials has good electronic properties. Since perovskite solar cells can be deposited on flexible substrates, so it is flexible solar cells. There are many disadvantages of using the perovskite solar cells. First is lead toxicity. Lead toxicity comes from the perovskite materials because to make the solution of perovskite uh, solution we use the lead as precursor material which are very harmful for our health. To make the solution of perovskite we also use the DMF and DMSO as solvent which are very toxic. And third, perovskite solar cells has low stability. It partially degraded in humidity and also by high temperature and UV light. So, perovskite solar cell has low stability. The main challenges to commercialize the perovskite solar cells are their stability issue in recent years. Moisture stability, light stability, thermal stability and electric field stability issue are the main stability issue in perovskite solar cell. Since perovskite material has organic material and organic material fastly react with the water molecule of moisture due to which it fastly degrades in moisture. The UV light present in solar radiation has sufficient energy to migrate the halide ions of perovskite material due to which it has low photostability. At high temperature, organic materials or molecules of perovskite are unstable at high temperature due to which it has low thermal stability. And high electric field is sufficient to migrate the ions of perovskite material due to which it has low electric field stability. There are many methods has been used by researchers till now to improve the stability of perovskite solar cells. One is hot casting. First is hot casting. In hot casting processing, perovskite layer is deposited in hot mode of solution and hot mode of substrate, due to which it forms large grain size, due to which its stability will improve. Other is compositional engineering. By compositional engineering, we can improve the quality or properties of perovskite materials like by using the compositional engineering we can passivate the defects due to which its stability will improve. Other is by modification of charge transport layer we can also improve the stability like moisture stability. Additive engineering has been also used by researchers to improve the stability of perovskite solar cells. Since by using additive we can passivate the grain boundaries and defects of perovskite layers due to which it has high stability. Luminescent downshifters has also been used by researchers to improve the photostability of perovskite solar cells, but that is limited hours for. In recent years, sodium chloride additive has been used by researchers to improve the stability of triple cation perovskite solar cells. Since sodium chloride additive passivates the defects and grain boundaries of perovskite layers, due to which its photo stability, thermal stability, and moisture stability improved. But that is limited for 1000 hours. To improve the photo stability of perovskite solar cells, we have synthesized a new type of pan-UV filters which acts as luminescent downshifters in perovskite solar cells. It mainly blocks the UV region of solar radiation and emits blue light. The pan-carbon quantum dots, which are used to fabricate the pan-UV filter, is synthesized after hydrothermal reaction at 200 degrees Celsius for 16 hours of washed material obtained after filtration of polyaniline. To make the pan-carbon quantum dots solution, pan-carbon quantum dots is mixed with polyvinyl alcohol and DI water in appropriate amount, and it is stirred with a heating condition at hot plate. To make the pan-UV filter, this solution is sprayed on glass, and by using a spin coating, we make the film of pan-UV filter, which is called the pan-UV filter or UV filter. To make the perovskite solar cell, we follow this process. Firstly, we take the FTO substrate, and after etching with zinc dust and hydrochloric acid, we got the pattern substrate. On pattern substrate, we take the solution of compact TiO2, and after a spin coating and annealing at 500 degrees, we got the compact TiO2, which acts as ETL layer in perovskite solar cells. And after deposition of compact TiO2 or on layer of compact TiO2, we deposit the perovskite, or we make the perovskite layer on compact TiO2, and this is triple cation perovskite material. And after annealing at 130 degrees Celsius, 100 Celsius, we got the perovskite film. And on perovskite film, a spiro is deposited, and after deposition of a spiro, it is taken for oxidation for 12 hours. And on a spiro, we make the electrode of gold by using the thermal evaporation. And by following this process, we got the configuration of triple cation perovskite solar cell with NIP configuration. So this is the chemical formula of triple cation perovskite material which is used in making of this NIP device. We have used different characterization technique to identify the properties of pan-carbon quantum dot, pan-UV filter, perovskite film, and perovskite solar cells. For film characterization, we have used high resolution scanning, tunneling electron microscope, field emission scanning electron microscope, atomic force microscope. So these three techniques have been used for surface morphology. XRD, Raman, FTIR, UV visual spectrophotometer, spectrofluorometer are also used to characterize the film characteristic on UV filter characteristics. For device characterization or JV measurement, we have used the catalyst source meter. For the external quantum efficiency of device, we have used Newport IQ200 instrument, and for defect density of fresh and degraded devices, we have used impedance spectroscopy. The stability testing of perovskite film panel filter and devices has been done inside inert atmosphere. For photostability, we have used one sun light, and for UV stability, we have 365 nanometer of 60 watt UV lamp. To identify the size of Pani carbon quantum dots, firstly, we have done the field emission scanning electron microscope of Pani carbon quantum dots film. It has shown 100 nanometer size of Pani carbon quantum dots due to the agglomeration of Pani carbon quantum dots. To identify the single Pani carbon quantum dots, we have done high resolution scanning tuning electron microscope. After observing HRSTM image, we got the size of Pani carbon quantum dot around 10 nanometers, and it also shows the graphic behavior of Pani carbon quantum dots. Graphic behavior of Pani carbon quantum dots also identified by the selected area electron diffraction pattern. This is the atomic force microscope image of Pani UV filters with carbon quantum dots concentration 3.988%. When carbon concentration inside Pani UV filter is increased, then its RMS value obtained by atomic force microscope will reduced, which shows that compactness of film or film quality will improve. To identify the functional group of Pani carbon quantum dots, FTIR spectroscopy of Pani carbon quantum dots was done. The peaks obtained at 1640 per centimeter confirm the quinoid ring present in Pani carbon quantum dots, which obtained after polymerization of aniline during hydrothermal reaction. This aniline derivative comes from washed materials after filtration of polyalanine. This is the FTIR graph of Pani UV filters. Pani UV filter is the composite material which obtained after mixing polyvinyl alcohol and carbon quantum dots in appropriate amounts. This peak obtained due to the formation of bond between carbon quantum dot and polyvinyl alcohol, CH stretching, which is at 2920 per centimeter, and quinoid ring slightly uh, displaced from original position due to the uh, formation of bond between PBA and carbon quantum dots. To confirm the UV absorption by Pani UV filters, we have done the absorption and photoluminescence of Pani UV filter. Firstly, we have done the absorption of Pani UV filter, which absorb the UV region of solar radiation from 295 to 400 nanometer. When this at this UV region, it emits the after observing this UV light, it emits the blue light around 450 nanometer. When this Pani UV filter excited with different wavelength from 295 to 390 nanometer, then its peak intensity will improve due to the improvement in number of photons in larger wavelength of UV light. When Pani carbon quantum dots concentrations are increased in Pani UV filter, then intensity of absorption will increase. Means the UV light absorbed by Pani UV filter increased. This is the photoluminescence of Pani UV filter at different concentration. When this Pani UV filter excited at certain wavelength in UV region, then Pani UV filter of type puff CQDS 3.98 weight% means the Pani UV filter which has carbon quantum dots concentration 3.98 weight% has highest photoluminescence intensity than other Pani UV filter. So this Pani UV filter is suitable for study the photostability of triple cation perovskite solar cells. To study the UV and photostability of perovskite films, firstly we make the triple cation perovskite films on glass substrate by a spin coating. Then one film is taken without UV filter and one is taken with UV filter. Then after this we expose the UV light. Then after degradation, means after exposure of 900 hours, you observe that without UV filter almost degraded due to the formation of pinholes, and with UV filter it almost remains same, which confirms that UV filter blocks the UV light. Similar observation was observed in one sun solar light. This is the XRD spectra of fresh and UV degraded films with and without UV filter. Without UV filter, intensity of XRD spectra reduced due to the degradation of perovskite films. This is the XRD spectra of fresh and UV degraded films with and without Pani UV filters, lies between 10 and 15 degree. This spectra confirms that intensity of perovskite films without filter reduced and it becomes more broad, which confirms that triple cation perovskite films degraded in UV light. This is the graph of region of crystallinity of fresh film and with and without UV filter. Means this graph showing the comparison of crystallinity of fresh triple cation perovskite films and UV degraded triple cation perovskite films Without filter, we observe that uh, crystallinity of perovskite film reduced from 78 to 62, but with filters it almost remains same. To study the UV and photostability of triple cation perovskite solar cells, firstly perovskite solar cells with NIP configuration, one UV filter is integrated on backside of glass. Then one sun radiation uh, passes through Pani UV filter. Then UV light blocks by Pani UV filter, and after absorption they emit the blue light. Visible light almost passes through the Pani UV filter. This is the field emission scanning electron microscope image of cross section of NIP configuration with integrated Pan UV filter. This is the normalized photoconversion efficiency obtained after JB measurement of NIP triple cation perovskite solar cells without filter and with different types of Pan UV filter to identify that which Pan UV filters improve the UV and photo stability and also gives uh, best normalized photoconversion efficiency. So we find out that Pani UV filter with 3.988% is the best Pani UV filter to study the UV and photo stability of devices, and also for JB measurement with Pani UV filter. So this is the current density versus voltage graph of perovskite solar cells with and without filter in reverse and forward bias. In reverse bias uh, with and without filter, current density slightly reduced due to the scattering and some absorption of photons of sunlight due to the Pan UV filter. The slightly reduced current density is also confirmed by external quantum efficiency graph of perovskite solar cells. This also confirms the current density obtained with and without Pan UV filters. To study the UV and photostability of triple cation perovskite solar cells with NIP configuration, two fresh triple cation perovskite solar cells fabricated at similar conditions are taken, one with UV filter and one without UV filter, and exposed by UV light of 365 nanometer wavelength inside glove box of nitrogen environment. And after this we measure the IV of these devices at regular interval of time. Then we observe that after 900 exposure of UV light, normalized photoconversion efficiency of triple cation perovskite solar cells with filter reached 0.90 and without filter it reached 0.14. This graph showing the JV characteristic parameter, means IB parameter of degraded perovskite solar cells without filter and with filter. Then we observe that photoconversion efficiency, fill factor, short circuit current density, and open circuit voltage of perovskite solar cell with filter is slightly reduced, but without filter it almost degraded. So we can say that the pan UV filter improve the UV stability of perovskite solar cells up to 900 hours. To confirm the or to observe the UV degradation with filter and without filter, we have done the impedance spectroscopy of degraded devices to measure the defect density of perovskite solar cells. Then we observe that without filter in intermediate band trap density increase as compared to with filter. With filter it almost remains same like fresh devices. Similar conditions are also observed for photo degradation. In photo degradation, we have also taken two fresh devices with filter and without pan UV filter and expose one sunlight for 1100 hours. Then we observe that uh, with filter photo conversion in normalized photo conversion efficiency almost remain 1 and without filter it reached 0.70. So we can say that it has photo stability beyond 1000 hour. This is the characteristic IV parameter of degraded perovskite solar cell with filter and without filter after degradation in one sunlight. Impedance spectroscopy also confirms the uh, degradation means defect density in fresh devices and degraded devices, which confirm that with pan UV filter defect density almost remains same and without filter its defect density increase in intermediate band. After synthesis characterizations and photostability, a study of films and devices, we conclude that we have fabricated Pani carbon quantum dots by hydrothermal approach from the washed material obtained after filtration of polyethylene. We have made Pani carbon quantum dot which emit blue fluorescence when excited with UV light. These Pani carbon quantum dots also have good transmittance in the visible range. We have made low cost biodegradable and room temperature processable LDS filter. This UV filter of type PUF CQDS 3.988% means the pan UV filter which have carbon quantum dots 3.988% absorb the UV light from 291 nanometer to 400 nanometer and show more than 80% transmittance in the visible region, which make it suitable UV filter for perovskite solar cell to protect the UV light. After a study of photostability and UV stability, we observed that UV stability Improve the photostability of triple cation perovskite solar cells more than 1000 hours. I am also thanks for science father. I am also thanks for organizing committee. I am also thanks for the excellent guidance and support of my supervisor Professor Ashish Garg and co-advisor Professor Kanwar Singh Nalwa. I am also thanks for supporting the solar group, material science and engineering department and sustainable energy engineering department of Indian Institute of Technology Kanpur, India. Thanks for your listening.